Welcome to AI Frontiers, your guide to cutting-edge artificial intelligence and robotics research. Today we're exploring 10 breakthrough papers in computer science robotics from September 13, 2025. These aren't just incremental improvements, but paradigm-shifting discoveries that span autonomous navigation, tactile sensing, cross-domain learning, and security advances. We'll examine real-world applications and future implications of research that's literally reshaping how robots perceive, learn, and interact with our world. Picture this: a robot delicately coating a solar panel while hovering 30 feet in the air, its sensors tracking every micro-movement as it navigates wind gusts and maintains perfect positioning. Meanwhile, across the lab, another robot is learning to fold laundry by watching thousands of hours of human videos on YouTube. And in a manufacturing facility, a security system uses nothing but overhead cameras to detect when hackers are trying to manipulate industrial robots. Sound like science fiction? These scenarios are all real, documented in cutting-edge research papers published just months ago. What makes today's episode particularly exciting is the diversity of challenges these researchers are tackling. We're not just looking at one narrow slice of robotics, but innovations that span from the tiniest tactile sensors that can feel like human skin to massive simulation environments that let robots practice dangerous maneuvers millions of times before attempting them in the real world. Each paper represents months or years of brilliant minds wrestling with problems that seemed impossible just a decade ago. Computer science robotics sits at a fascinating crossroads where multiple disciplines converge. It's where computer science meets mechanical engineering, where artificial intelligence shakes hands with electrical engineering, and where pure mathematics dances with messy, unpredictable reality. Unlike most software that lives in predictable digital environments where 2 plus 2 always equals 4, robots must navigate our chaotic physical world. They deal with sensor noise that makes their eyes and ears unreliable, mechanical imprecision that means their movements are never quite perfect, and the inherent unpredictability of real-world scenarios. Imagine trying to write a program that can perfectly catch a ball thrown by a child. This is the reality that robotics researchers face every single day. The first major theme revolves around autonomous navigation and localization in complex environments. This goes far beyond the fundamental question of, where am I, and how do I get where I'm going? The photovoltaic panel coating quadcopter demonstrates sophisticated visual inertial odometry for precise positioning near solar installations, while the Nav-R1 system combines high-level reasoning with navigation for embodied agents operating in three-dimensional spaces. Think of it like the difference between a GPS system that just tells you turn-by-turn directions and a human navigator who understands the context of the journey, can adapt to unexpected road closures, and knows when to take scenic detours. The second theme centers on learning from demonstration and human-robot knowledge transfer, exemplified by the ImMimic framework developed by Liu and colleagues. This breakthrough enables robots to learn manipulation tasks from abundant human videos, like teaching a robot to cook by showing it thousands of cooking shows. But the challenge is that the robot has different hands, different sensors, and different physical constraints than the human chef. The breakthrough lies in bridging these domain gaps effectively, potentially revolutionizing how we train robotic systems by leveraging the vast amounts of human behavioral data available through video platforms. Our third theme focuses on advanced sensing and perception systems that could fundamentally change how robots interact with the world. The scalable tactile sensing architecture demonstrates how robots can achieve human-like touch sensitivity across large surface areas, enabling them to feel texture and pressure across their entire body surface, not just at their fingertips. Meanwhile, cyberattack detection systems show how computer vision can provide independent verification of robot sensor data. This opens up entirely new possibilities for safe physical interaction and robust operation in critical environments. Let's examine the first key breakthrough: solving the quadratic scaling problem in tactile sensing. Traditional approaches to large-area tactile sensing face a nightmare scenario, where adding more sensors exponentially increases wiring complexity and reduces response speed. Imagine trying to wire a house where every new light switch requires connecting to every other switch. The complexity quickly becomes unmanageable. The orthogonal digital encoding approach fundamentally solves this by enabling thousands of sensing nodes to communicate through a single transmission wire while maintaining sub-20 millisecond latency. This could enable robots with truly human-like tactile capabilities across their entire bodies. Today's paper of particular interest comes from Liu and colleagues, who tackled what seems like an almost impossible challenge: teaching robots to perform human tasks using only videos of humans. The fundamental problem is beautifully simple, yet profoundly challenging. While humans perform countless manipulation tasks daily, creating vast repositories of behavioral data through videos on platforms like YouTube, Instagram, and TikTok, robots traditionally require their own demonstration data. This creates a massive bottleneck. Imagine if every time you wanted to teach someone a new skill, you had to find someone with exactly the same body type, height, and physical capabilities to demonstrate it. The researchers' breakthrough lies in their elegant two-stage process that bridges the substantial domain gaps between human and robot embodiments. First, they use dynamic time warping to establish correspondences between human hand trajectories and robot joint movements, handling the temporal misalignment that naturally occurs when different embodiments perform the same task. The second stage applies mix-up interpolation between the paired human and robot trajectories, creating synthetic trading examples that lie in intermediate domains. Think of it like creating a smooth gradient between two different languages. Instead of jumping directly from English to Mandarin, you create intermediate steps that help bridge the gap. The ImMimic framework's experimental validation spans 4 real-world manipulation tasks across 4 different robotic embodiments, from robotic grippers to Allegro hands. The results show not just improved success rates, but dramatically better execution smoothness, indicating that the learned policies are more natural and human-like in their execution. What makes this work particularly significant is its potential to leverage the vast amounts of human behavioral data available through video platforms. The inspiration came from watching a young child learn to tie shoes by watching YouTube videos. If a child can learn complex motor skills from watching others, why couldn't robots do the same? Looking toward the future, these research directions paint a picture of robotics that's simultaneously more capable and more accessible than ever before. Think of the current state of robotics like the early days of the Internet. We have the basic infrastructure in place, but we're only beginning to glimpse the transformative applications that will emerge. The convergence of these research themes suggests exciting possibilities. Robots that combine tactile sensitivity with advanced learning capabilities. Robot surgeons that learn techniques by analyzing thousands of hours of surgical videos, and security ecosystems that make robotic systems more reliable than human-operated alternatives. As we wrap up today's exploration, what strikes me most is the convergence happening across these different research areas. We're not just seeing isolated improvements in individual capabilities, we're witnessing the emergence of a new generation of robotic systems that are more capable, more adaptable, and more trustworthy than anything we've seen before. The papers we've explored represent building blocks for a future where robots become true partners in human endeavors, from delicate caregiving to precision manufacturing, augmenting human capabilities rather than replacing them. This content was created through AI synthesis using GPT Anthropic Claude Sonnet 4 for analysis and narration, TTS synthesis via Deepgram technology for audio generation, and image generation through OpenAI systems. All content has undergone human expert review, though we acknowledge the potential for oversights in this rapidly evolving field. The research papers discussed are available on the archive preprint server, and we encourage listeners to explore the original sources for complete technical details. Thanks for joining us on AI Frontiers. Subscribe for daily coverage of cutting-edge AI and robotics research. Explore these papers yourself, engage with researchers online, and share your thoughts on these breakthrough developments. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive-preprintserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive-preprintserver.org.